Hi there, everybody. So today's lecture, we're going to look at section 1.7. For those of you who have finished the other three homeworks, good job. I don't recommend even starting 1.7 or 1.6. The order is 1.7 and then 1.6, the way we do it. Because these homeworks starting with 1.7 and 1.6, these homeworks aren't due for a whole other week. So you want to make sure that you completely have finished all of the other four homeworks before you jump into this stuff. And the reason for that, and the worksheet, I posted an activity worksheet in Canvas in the files section. That's just something for you guys to work on. You will actually have the solutions to that at the beginning of next week. So let's look at section 1.7 now. So this is, for many students, this section is one of the harder sections, but only because it doesn't look like anything you've ever seen before. It's not fancy, it's just precise. So the homework does a great job of walking you through all the various options. I'm only going over two of the options today. And your online resources are really, really fantastic for getting to know this. So I'm going to do a couple of the slides in the PowerPoint. Then I'm going to jump over and show you something that the ebook has. If you haven't been using the ebook resources, this is a great time to start using them. And then we'll complete the first two exercises. And then that'll be it. So trying to keep these videos at around a half an hour, at least early on while you guys are still getting the hang of the course. Later on, the videos are going to be longer. But for now, they don't have to be, right? All right, so let's, normally I don't just sit and read the PowerPoints, but the thing is, we had an intuitive definition of a limit in the previous sections, right? Where we did a bunch of work about what happens if your x-coordinate gets closer and closer to some number. Well, then your y-coordinate should also get closer and closer to a different number, and we call that number L, right? So it just means that, the limit exists if moving x toward A causes your y-coordinate to move toward L, right? But what does that mean precisely? So that's what we're going to look at today. So here's our precision definition of a limit. Get to know these pictures, folks, because, and as soon as I'm done reading this slide, I'll show you the visualization. So the idea here is just that we have some function, some wiggly function that does something. And the idea is that, up to this point in the first two sections, we would come in closer to A on the right, and we would come in closer to A on the left. And we would look and see what happens, right? So if we come in closer to A on the right, the function comes up and gets closer to L. And if we come in towards A on the left, the function comes down and gets closer to L. Great. But that's not a proof, right? We have very, 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 very strong evidence based on our tables and our graphs that a function like this, that the limit would exist everywhere. But we've also seen that there are some weird functions out there, right? And generally speaking, in calculus, we're not really that concerned with all the super crazy functions. But you never know when one's going to pop up, so you have to have techniques that work all the time. So this precise definition of a limit is a proof. There's two different proofs that we're going to see today. One where you're just finding a value of this delta down here. And another one where you're proving that the limit exists at some particular point. So let's see how that works. So just a couple terminology issues we got to look at here. So this is called epsilon. It's a Greek epsilon. It's kind of like a fancy Greek letter, actually. And then here's lowercase delta. So if you're trying to like keep all this stuff straight, there's two ways. There's two mnemonics for remembering this. D comes before E in the alphabet, and X comes before Y in the alphabet. So D delta goes with X, and epsilon goes with Y. So that's easy to remember. The other one, the other mnemonic is that E can be thought of standing for error. So this is used a lot in like manufacturing technology and stuff, where if you have to make some sort of machine part, you'll have a certain amount of tolerance or error on the machine part. And if you're like designing a control system, the input would be like your delta. You'd have to decide how much error on the input am I allowed to have to maintain a certain amount of error on the output. Remember, your y coordinate is your output and your x coordinate is your input. So D, you can think of it as standing for distance, if it helps remember. So you have a certain amount of distance that you can be away, and you're trying to get within a certain amount of error tolerance. So two ways to remember delta and epsilon there. Anytime you do a problem, remember this graph or the one I'm about to show you, okay? So here's the definition of a limit. Oh yeah, let me do two more slides, and then I'll show you the visualization, and then I'll do the examples. So here's the precise definition of a limit. It's very, very precise. So again, the idea is just f of x is a function, right? And it doesn't have to be defined at that point A. If you go back a slide, you can see here that A actually has a hole in the graph again. Remember, when we do limits, it's never required that the function is defined at this particular point A. So the precise definition says the limit of f of x as x approaches A is equal to L if for every number epsilon greater than 0, there is some number greater than 0, some delta greater than 0, such that if, so I'm going to read this just sort of the way it look, so if 0 is less than the absolute value of x minus a is less than delta, then the absolute value of f of x minus L is less than epsilon. A lot of symbols, but that's not really how we interpret this. Instead, you can always interpret absolute value, when we're talking about graphs, you can always interpret it as distance, right? Because distance is always positive. So what are we saying here? Well, we can ignore this 0, because we already know delta is positive. Okay, so just this 0 is here just so that you don't accidentally make it negative. Like if you forget the absolute value when you're doing problems, you could switch those and get a negative number, and you might go, oh, I've satisfied, look, negative numbers are less than delta. But you just got to make sure that you're remembering the absolute value here. So this is saying the distance between x and a, remember, x is just any number on the x-axis. So the distance between x and a is less than delta. So if this is true, if we've successfully found this delta where if x minus a, that distance, is less than delta, then the resulting y-coordinate difference will be less than the pre-specified value of epsilon. This will make a lot more sense once you see some more examples. And this is what the graph looks like. So here, all I did is took the picture from a couple slides ago and just recast everything with the new language. So what does it mean? 0 is less than, what does all this mean? Well, remember the rules of absolute value. You can rewrite this expression as this expression. Right? That's what absolute value does, right? It's plus or minus. Well, this is just this down here. Look. Here's a minus delta. That's this point here. Here's a plus delta. That's this point. We're just saying when x is in here somewhere, right? So this thing gets unpacked to read like that. Okay? Now, you can do it with algebra, but clearly that's the same meaning. You can see that it's the same meaning. So, the distance between x and a is less than delta. Right, it's in this area. And if we can find a delta where this is true, in order to successfully show that the limit exists, then that would have to also satisfy this. So if this is true, then this is true. That's what we're trying to do. And we have to find delta. That's our goal for the first exercise. For the second exercise we're going to do today, it's actually a different kind of exercise. It's a proof. So here we go. Let's look at, all right, so we got the x's. Now let's look at the y coordinates here. It's just the same thing. It's just on the y-axis, right? It's the same picture as this, just on the y-axis. So we're saying if we can find delta, then when x is in here, f of x is going to be in here. So let's see what that looks like. All right, so this is one of the visualizations in the textbook. So I found one that looks sort of similar to the example that I have in the notes. And the idea is, in calculus, we want to show that this is true all the time. So look at the definition again. For every number epsilon, again, these have to be positive, right? There is some number delta where this rectangle is true, is green, right? Because if I open these deltas up, it turns red. That means I failed to find delta where this is true. Okay, so these are just numbers. These are, like I said, I just slid this around and got some decent looking numbers here. And you guys can goof around with this and just mess with it until you think you understand it. It takes a long time. Now, some of you are going to look at this and just immediately understand it. And for the folks who have already taken calculus, you probably remember this stuff. Okay, so what can we do with this? Well, let's go back and look at this precise definition. And let's see what does it look like? Like, you know, so does the limit exist at every point on this graph? Like, we don't know. So the idea is we can just, it says for every number epsilon. That means I should be able to move this thing around. I'm just going to pick any number. Let's pick a really small number. Now let's move it around somewhere, I don't know. Let's move it right here. So if this is my requirement, again, pretend like you're a manufacturer or you do computers for a manufacturing company. We need to make golf balls that weigh a certain amount. Our machine has to have a certain amount of tolerance. Can we build a machine to the right specifications to get our golf ball weights to be in this region? Don't know. Let's see. And so you just wiggle this thing around. Well, this is making it bigger, so that's no good. Now look here. I came in a little bit, and you see that this one is red, but this one disappeared. So what that means is that depending on where you're at, you might get different answers. You have to keep going until the entire rectangle turns green. And what you want is the largest value of delta where that rectangle turns green. And you can see, I can't really zoom in on this anymore, but you can see here that it's intersecting, and here we're actually to the left. And you can just goof around with this. Just slide this thing around. Try to find places where... So here's another one. Just made this one up, right? My tolerance is 1.51 units. I'm centered at this value, 1.61. Can I find a delta so that this y-coordinate interval will be satisfied? Well, just slide it around. You can see on the left side, it's already satisfied, right? Because there's no intersection point here. So we're good on the left side. Just got to keep moving till the right side turns green. And there you go. Okay. So that's really what you're going to be doing, but you're going to be doing it with algebra to some extent. On an exam, I'm not going to have you get in here and mess with this thing. This is more for just understanding the concept of a limit. So if your function is in fact continuous, and continuous in the sense of what you're going to see later on, you might think that means that the limit always exists. But that's not true, right? I don't think there's any in here that the limit doesn't exist, actually. Yeah, so the limits actually exist on all these. So you're in good shape. It just doesn't have a zillion options. Right, so here's another one, right? So we can do this one. And you get the idea, right? So can we, can I find delta where this thing's definitely true, right? So if here's a big delta, keep bringing it in, bringing it in. As soon as those red dots go away, it'll be satisfied. Oh, there's another red dot. And you can make this thing as small as you want. Will it ever turn green? Yep. It's just super small, right? And that's the idea. So we already saw functions earlier in section 1.5, right? Well, we had the sine of 1 over x. That just gets super wiggly in the middle, right? That limit would not exist, right? In fact, that's what we decided, right? That the limit does not exist as you come in towards 0. It's because of this epsilon delta concept. Because if you pin down a certain y-coordinate, the thing just keeps getting more and more wiggly. So the limit doesn't exist. And that's actually the definition that we used. I think all the rest of these are fine. Okay, so that's it for the visualization. Now let's get into the problem-solving side of it. If you get confused or lost while you're doing the homework at any time, there are some more in-depth study tools and stuff at the end of the slides like we've been doing. The stuff in the textbook's really great. The online textbook. It's really, really great. Feel free to use that, right? And a lot of the problems on your homework are the same ones that are in the book, just with different numbers. So you might as well go get the answers for free, right? Nothing wrong with free answers. As long as you understand it, and if it's on a test, you can do the work, you're good to go. All right, so let's jump in. Let's do the first example here. So use a graph to find the best choice for a number delta such that the following holds. So this is just the formal, way to write it. So if the absolute value of x minus 1 is less than delta, then the absolute value of the function minus 2 is less than 0.2. So what we want to do is match up everything in our problem with the numbers in the definition. So again, let me go back and show you the definition. Right, here's your definition. So whatever number goes with x is what we've been calling a. That's where that's where the limit is approaching. Right? The limit as x approaches a, right? And then L, that's our y-coordinate limit. So the two numbers that appear inside the absolute value are, here it is right here, are a and L. So all we have to do is match everything up, right? So look here. So 0, x minus 1 less than delta, 0, x minus a less than delta. So a must be 1. So just write a equals 1. You're pretty much going to have to do it this way. You want to identify every single piece. All right. Now we have these two things here. There's going to be a minus sign over here somewhere. That minus sign will correspond to this. Everything on the right is L. Everything on the left is f of x. Remember, L has to be a single number. F of x is going to be a function. And last but not least, we have epsilon over here at 0.2. Now, as you notice, delta stays delta because we're trying to find delta, right? Like what we did here, right? So what we do is we pick an epsilon, whatever it happens to be, and then we look for delta. Is there a delta that turns the box green? As soon as we find the largest value of delta that will turn the box green, we have succeeded. This slider thing in the textbook is not precise enough to do the homework, just so you know. You are going to have to use your calculator to do this. Because a lot of times the homework wants you to round everything to 3 decimal places and stuff, and sometimes this isn't that accurate. All right, so notice what I said here, right? We match up the given values with the precise limit definition, and so you just label everything. A, f of x, L, epsilon. So there's 5 values. We know 4 of them. We're looking for delta. So then what we do is we take those values and look at what we're trying to show. Right? Our desired result is that this difference will be less than some epsilon, right? Sort of like what I have in the graph. It's not the same function, but it doesn't matter if it's the same function. Oh, here's the function. Okay. Again, it's not quite precise enough, right? But I can build it, right? So go here. Look, so A is 1. Right? So let's move this to 1. Yeah, not quite precise enough. It's close. I don't know how to get it more precise. Oh, there we go. I got it. All right. Let's see here. What else we got? Oops. Oh, here we go. We got the function L is 2. Right? Yeah, because you can see the 0.12. Right? So, and epsilon is 0.2. Maybe this one is precise enough. Let's see. There you go. So this is what we're trying to do. We're trying to find delta. We're trying to find the delta where this thing turns green. That's it. It's exactly what we're trying to do in this problem. Again, the online simulator is not precise enough. Okay. So what we do is we take our desired result. We want this distance between f of x and L to be less than epsilon. So we plug everything in, right? We know L, we know epsilon, we know f of x. Just plug in everything you know. And then simplify. And then you end up with this, right? So this is what's shown over here in this graph, right? The function itself, so the thing in the middle will be the function, is between 1.8 and 2.2. Those are these y-coordinates here, 1.8 and 2.2. So we want to find the values of x that result in the values of the endpoints of this interval. So we have to solve for x to find out what values of x give us 2.2 and what values of x give us 1.8. If you know the cubic formula, I did not put it in any of the notes. You're allowed to use it, but there's an easier way to find intersections of functions, right? That's what we have graphing calculators for. So on a graphing calculator, graph all 3 of the following. So let's do that now. Okay, so we're going to go into our grapher, and whatever your function is, the lower horizontal limit, the upper horizontal limit, and then we're going to have to find a window, right, that works. So let's go ahead and do that. So the function is x cubed minus 5x plus 6, right? X cubed minus 5x. Oop, messed that up. Let's try it again. X cubed minus 5x plus 6. Then you want to type in L minus epsilon, which is 1.8. Then you want to type in L plus epsilon, which is 2.2. And then use a domain suitable to your problem. We don't know what the x values are here, right? But we kind of have some idea, right? So what I'm going to do is select a fairly large x interval around x equals a. All right, so a in this case, for this particular problem, a is 1. So I want to pick something around 1, fairly large. So I'm going to go like -2 to 4, right? That's a fairly large interval. Because we saw the graph. We know that that's big enough, right? And then I'm going to use zoom fit to do the rest. So I picked like a fairly large x interval. That will guarantee that the graph shows up. Then I'm just going to zoom fit, which is sort of annoying, sort of far down here. You can just type in 0, but it's 0 for zoom fit. Go ahead and click that. The calculator will do everything else. Right, we already know what the function looks like. Should intersect twice, right? So we can see that this function does indeed intersect. Now we want to sort of zoom in on that. So you notice I picked my x interval way too big, so just do it again. Let's pick a much smaller interval. So how about like negative 0.8 to 1.2? And then just repeat the process. Remember, you don't know where this graph is going to be, right? We've seen already, and I'm sure you guys have seen this stuff in the past, that you can't just guess. Oh, sorry, not negative 0.8. 0.8. You can't just like guess, right? So now it's a smaller interval. I'm going to do the same thing again. I'm going to zoom fit. I just hit 0. If you guys want to do that, just hit 0 and it'll do it automatically. So you can get a pretty nice graph pretty quickly, just with a little bit of trial and error. Don't be in a big hurry, guys. Accuracy is the most important thing, because on a test, this is what you're going to have to do. Okay, the colors are all switched because when I built this thing, I used a different program, but you can change the colors around in here if you want, if you guys have a calculator that looks like this one. But the function is the blue one, and the top and bottom line are these two. Now, we're going to use the calc intersect command to find the intersection points. So let's do that. Okay, so calc is up here, right? So second calc. There we go. And we're going to choose intersect. So you can just hit 5, right? Now what you do is you get a little flashing thing. The way you use this is you go near an intersection point, go to the left of the intersection point, then go to the right. And then you tell the calculator there's an intersection somewhere between these two values. So you got to like scroll to the left. You can also type numbers in if you want. So if you know like kind of where the number is, you can actually type it in. So here we go. I am to the left of the first intersection. So I'm going to hit second curve. Just go down, right? Second curve. So what I did, I selected the first curve. You want to go near, but either a little bit to the left or a little bit to the right. Could have gone to the right. Select the first curve, select the second curve. Then it says guess. Anywhere close is fine. So the intersection is 0.911. Now we're going to do it again. So you write that number down, and then we do this again, right? You actually have to go back out and do calc intersect again. Right? So we do it again on the other one. Not that. Oh, I hit the wrong button again. There we go. Same sort of thing, right? Just scroll way over. So all you have to do is just be close to it. You don't have to be super duper close. The curves I'm giving you guys for the homework are not tough curves. Okay. Let's just hit enter. And then second curve, hit enter again. Guess, just anywhere close is fine. It'll get it right. We're actually, later in chapter 2, we're actually going to learn the method that the calculator uses to find these intersection points. 1.124. So we had 0.911 and 1.124. That's our two intersection points. So now we have x coordinates on the curve. Any numbers in between there satisfy the epsilon delta proof, right? So you just write those down, right? So here I just rounded them. Oh, here it is. Right here. Oh, yeah. I rounded them to 3 decimal places, right? So x is 0.911 and the other one was 1.124. And you can see that the graph that I printed out here looks really similar to this one. So in the notes, it tells you what interval to use. When you guys are doing the homework, you're not going to know what interval to use. Start fairly large and then just move in and just keep zoom fitting and it'll find a good window. You need the window to look fairly nice so that you can find these intersection points. This is the only way to do these problems, guys. Let's keep rolling. So are we done? We found the intersection points, but are we done with the problem? So let's go back and look at the beginning of the problem, right? The problem says that that we need to find delta. We haven't found delta. So how do we find delta? Well, the way this works is we know that the absolute value of x minus a is delta. We know x, we know a, so it's easy to find delta. Notice we need to use absolute value here, right? This is that thing I told you about. If you forget the absolute value, this is going to be negative, and it doesn't work if it's negative. Okay, so just be careful. So we get, you just go ahead and do the arithmetic on a calculator or whatever. You get 0.911 minus 1 is 0.089. And then you do it again for the other one, you get 0.124. So what we found is if you use this left endpoint here, this left intersection around A, it tells you delta is 0.089. If you use this right intersection, it tells you 0.124 is delta. Because it's a curve, right? It's not a straight line, so if you go out on either direction, you're going to get different answers depending on which side you go. We pick the smaller of the two distances, right? And we saw why that's true. Oops. Right? We saw why that... So I'm going to make epsilon bigger, just so you can see what's going on, right? So we saw why you need to pick the smaller distance, right? Because if I stop here... So here we have an intersection point. But over here... So this is telling me that delta is 0.5, right? If my epsilon is 1.6 on this function, oh yeah, here we go. So if we pick A is 0.5, epsilon is 1.6, and delta is 0.5, this is telling us that here we have an intersection point, but this doesn't work as delta because there's a little bit of the function that's above L plus epsilon here. You need to keep making that smaller and smaller until the box turns green. So here, this is the smaller of these two distances, right? So this green rectangle here corresponds to delta being 0.325. And this one, the bigger one, corresponds to being 0.475. You always pick the smaller number. So for the problem we were doing in the notes, we always pick the smaller distance, which is 0.089. So that'd be your answer. So if this is a homework problem, this is how you do this homework problem. If this is on a test, this is how you do it on a test. Word for word, precisely like this. If you guys are looking for easier ways to do these problems, they really don't exist because I'm testing you on an exam. I'm going to test you on your knowledge of the process. Because if you know the process, it means you understand the concept. Okay. So to finish the whole thing off, all you do is you just sort of rewrite the thing just as a formal statement of a fact, right? So delta that we found in the problem was 0.089. So then you just rewrite everything. So if the absolute value of x minus 1 is less than 0.089, then, and so we've satisfied the second half of the inequality. So this is the delta we needed to make this a true statement. And the precise definition of a limit says, if the limit exists, then for every epsilon, we'll be able to find some delta. Right? So this is just showing it works for a particular value. So if you can find that it works for any value you select, so this is just some value, then the idea is that that should make it believable that it works for all values. Because if you think, oh, I bet there's some number up there that if I pick epsilon, then delta just won't exist. Well, that's not true, right? We saw that for this particular problem, it's always going to work, right? Because of the way the graph looks. If you bring those together, you're going to be able to bring the x-coordinates together. And again, always select the smaller distance. So that's example 1. Moving on to example 2. Now we're going to do an easier function, but we're going to use algebra. So our first example was just an illustration of the definition of a limit. for a given value of epsilon, but we need to prove that for every value of epsilon, there is some delta. So what we're going to do is pick a much easier function. We're not going to use a cubic function because, as you saw, you can't factor cubics. I mean, you can, but they get super ugly, right? That's not what we're here to do. We're here to just make sure that you guys understand the concepts and can show me on a test. We're not doing a bunch of algebra jumping through hoops, right? Okay, so what we're going to do, the problem we're going to do, all right, don't need this anymore. So the problem we're going to do is prove that the following limit exists. So we're going to show for every choice of epsilon that we can find some delta to satisfy the precise definition of this limit, right? So there's two steps to this proof. The first one is just like a preliminary analysis that uses algebra. And that will give us a value of delta. Then the proof itself is saying, if we use this calculated value, then this statement at the bottom will be true. That's the idea. It's kind of a long process. It's not super difficult algebraically, but you have to really follow along with where we're at. So this is what we're trying to do, right? For a given epsilon, we wish to find some delta. It just has to exist such that, and this is our precise value of the limit, right? So it just means that if you know epsilon, I need a formula that will tell me what delta to put in here. And then if I use that delta, then this statement will be true. So we actually have to kind of work backwards and then find that value and then go back and plug it back in and check it. So notice here, right, epsilon is not given, so we need to estimate delta in terms of epsilon. So here's the general method. You need to manipulate everything inside the absolute value over here in order to get an x minus 1 to appear. The reason you do that, if you can factor an x minus 1 out of here, then you can replace that x minus 1 with a delta. And if you put a delta in over here, you will have delta in terms of epsilon. And then you can solve for delta. And that's what we want to do. So this is how you do it. All right, so we manipulate the epsilon inequality until you get that quantity on the left of the delta inequality, absolute value of x minus 1, alone on the left-hand side. These manipulations, it turns out, are pretty easy, and they always work because we're doing linear functions. Linear functions can be manipulated to factor out anything you want. So just follow the algebra, right? You can see what we're going to do. We're going to get a common denominator. Then we're going to do this. We're going to subtract the fractions, and then we're going to simplify, right? So you get this. So we start on the left-hand side. Common denominator is 3. Subtract the fractions. Simplify. Now you can see that there's an x minus 1 up here. And because that x is a variable, we have to leave it inside the absolute value. You're not allowed to pull variables outside of absolute value. You're allowed to pull numbers out, though. So we can pull that 2/3 out of the absolute value. Right? So you factor the 2 out, and then we have a 2/3. That 2/3 can come out of the absolute value. And now look at what we have. We have what we want, right? 2/3 times some quantity is less than epsilon. Now I can use what I had on the previous slide. Now I can use this expression and back substitute delta in. And that's actually what I'm going to do. Right? Again, this is still the preliminary analysis. You'll see how it works here in a second. I'm not done yet. Right? So look at what we have. We left off with 2/3 times this quantity is less than epsilon. Clear everything from the left-hand side. So just multiply by the reciprocal, right? Multiply by 3/2. And you end up with this. So this is sort of where we want to be. We've done the first part, right? We manipulated this until x minus 1, absolute value of x minus 1 is alone on the left-hand side. Now what we do is we just match the two things up, and we say, if we're trying to do this, and we know this is true, doesn't that mean that delta must just be 3/2 epsilon? That's exactly what it means. So you have two inequalities that have the same left-hand side. That means that you can match up the right-hand sides. And that's what we're doing. So again, just to review. We want this, we want this left-hand side to look like this left-hand side. As soon as we do that, we can just set this right-hand side equal to this right-hand side. And that's what we're going to do. Right? That's what we did actually, right? So this suggests we should choose delta to be 3/2 epsilon. Once we've done the preliminary analysis, you move forward with the proof and you say, if epsilon is a number, we choose delta to be 3/2 of epsilon. And it always works. Okay. And so here's the proof, right? So given epsilon greater than 0, we will choose delta to be 3/2 of that value. And then you have to prove that it works. So we just go through the algebra again. And when we get to the final step, we just plug delta in and show that it is a true statement. So this is our beginning, right? This is the left side of, this is the first statement of the precise limit definition. So we need to show that if we have epsilon and we choose delta to be 3/2 of epsilon, what happens? So all we do is we just go through, simplify it as much as you can. This is exactly the same algebra you did in the first preliminary analysis. But when you get to the end here, when you get to 2/3, when you get to that 2/3 times that quantity, you take this whole quantity, and that has to be less than delta. But we're saying delta is 3/2 epsilon. So you just plug the 3/2 epsilon in where you have this inequality, right? So what we're saying is that, let me just go back and show you again what we're saying. We're basically saying, and you can ignore this 0 for now, just because it has to be positive. We're saying if absolute value of x minus 1 is less than delta, then then 2/3 of this is less than 2/3 of that. Right? You can multiply both sides of an inequality by 2/3. And we're saying delta is actually this. So we're just taking this whole thing with this plugged in here and replacing that expression with this expression. Because we have to preserve the inequality, right? There's no way to work backwards and solve this. You have to, as soon as you get the 2/3 here, just take whatever delta is and plug it in here, and it works every time. So 2/3 times 3/2 epsilon is in fact epsilon, and that's the proof. So it might seem like we just did this proof twice, and in a lot of ways we did. The reason I use these types of proofs to illustrate this concept, there's two reasons. Number one, there are more complicated versions of this stuff in the real world. I just wanted to show you two examples of things that I think capture sort of the essence of early calculus, which is, how do we know something is true? You either have to make a table or make a graph and just show that it's believable, right? That's what we did over here when we did this first problem, right? Or you have to actually do a proof with algebra. Those are the only ways we're going to be able to verify the truth of something, right? Table, graph, proof, like algebraic proof. It's basically it. So these two examples use a lot of the techniques that we use a lot in this class. So everything you have on the homework looks something like one of the two problems I just did. If you're trying the homework and you're getting, mixed up by something or caught up, you can't figure something out. Remember, guys, you have all of this extra practice stuff that if you're not 100% on board, go do some of this stuff. Get in there and fiddle around with the epsilon delta graphs. Get in there and look at the online homework, the homework tutor here, right? Because there's a couple problems on the homework that, are more challenging, and I'm not covering them in the lecture. I just don't have time, right? You guys don't want to sit here for hours and hours and hours, and you might already be doing that. Instead, you gotta take it upon yourselves to work from home. And if you are getting hung up on one or two problems, jump in there, look at that homework tutor. There's a good chance, or at least a 50-50 chance, depending if it's an odd problem or an even problem, there's a 50-50 chance that there's going to be an explanation of that homework problem using the ebook and that homework tutor. So all this stuff is great. All these resources from the textbook are great. And of course, you can always use the free online resources. Any of those are fantastic. Khan Academy does a great job. It's, any of these resources. It's called an epsilon delta proof. And for those of you moving on to more difficult math classes after calculus, you'll see stuff like this farther along in your math careers. So that's the end of today's lecture. If you have any questions, let me know. And I'll see you guys at the next video.